Hey everyone! So in this video I'd like to talk about function composition. So there are many ways we can put functions together. Some of the common ways that you might have seen before through our typical operations like addition, subtraction, multiplication, or division. And maybe just to go over an example, I can imagine taking my function f of x and subtracting away my function g of x, right? I can take the output from f, which is 3x minus 7, 3 times the input, take away 7. And I can subtract away the output for g of x, right? And so that output's given by x squared minus 1. Right, and so what we get out is, well, that's 3x minus 7, take away, we're subtracting away this whole x squared minus 1, so that's x squared plus 1. And we get out 3x minus 6 minus x squared. And so this is an expression that can be used to tell us the output of f take away g of x. Right, evaluate f, evaluate g at that same input, and then subtract the two away. This expression tells us the same result. And similarly, I can take f of x, and I can divide away g of x. And really that just means, take my f function, my output for f, and divide away my output for g. And so another way we see this expression called, or be referred to as f over g of x. It's the new function that tells us what we get when we evaluate f, evaluate g, and then divide the two results, right? So we can put together these two functions through division. But another common way we can put two functions together is to take the output from one function and use it as the input for the other. So for example, if I take my f function from above, I can imagine plugging in the number 4 into it. Right? I'm just kind of picking this number arbitrarily. I'm plugging in the number 4 into my function f. Well, my f function tells me take 3 times my input, so 3 times 4, and subtract away 7, right? That's how we defined f above. And so, working this out, we get 3 times 4 is 12 minus 7. Our result here is 5. So what I can imagine doing is I can imagine taking this result and plugging it into my other function, taking the output of this function and plugging it into my other function here. So here I can take this and plug it in to my g function, and what that function does is it squares the input and subtracts away 1, so we square 5 and subtract away 1, so that's 25 minus 1. The result is 24. And so this happens quite frequently, and we give this the name of composition. Now, one thing before I really define composition a little bit more explicitly is one thing to take away is that this 5, this result from this first function, notice that we can kind of think of it as f of 4, right? F of 4. The output when we plug in 4 into our function f, that is 5. And so a way we can be more suggestive about what we're doing here is we can really imagine that g of 5 is really the same as writing g of f of 4, right? Because this was that 5 here. Maybe I'll write it this way. Okay, so using the output of one function as the input of another, this is called function composition. And so the notation we use for this, kind of based on what we wrote earlier, is we write g of f of x to convey inputting the result of f into the function g. Right, so here, this phrase here, this statement here, this can be read as g of f of x. Oops. Or you can kind of think of it as also saying g composed with f. Some other notation for it, and so maybe I'll include it in the same description here, is sometimes you'll see it written as g with this like sort of open circle here between the other function f, g composed with f of x. So the main idea here is that really this is describing input into f, and then use this output as the input for g. So we sort of work inside out, right? We sort of deal with this interior f of x first and then input that result in this outer function g. Another thing I want to emphasize is that here, this composition symbol, this open circle, this is not multiplication. It's not to be confused with multiplication. This means composition. This just means input of one function into another. Okay, so let's go ahead and practice composing two functions using these two tables below. So for this first example, I want to compute f composed with g of 6. So we want to evaluate g, our g function here. We want to evaluate it when the input is 6. So we get out 4, and then we're going to plug that result into our f function. Right, we're working inside out. We're going to plug into our f function 4 to get 1, right? So really, maybe I can rewrite this in a few different steps. So this is the same as f of 6, or not f of 6, this is the same as f of 4, right? G of 6 is equal to 4, so this is the same as f of 4. And then f of 4, well, this is equal to 1. Okay, and then if we take this same statement and we reverse the composition, we reverse the order, and we sort of run 6 through our f function first, what do we get out? Well, f of 6 takes the input of 6 and it brings us to 3, right? So this is the same as g of 3. And then we're going to take that input of 3 through our g function to get out 6. Right? G of 3 is equal to 6. And so one thing I really want to emphasize that's hopefully illustrated from this example is that changing the order of composition, whether you go through G and then F, or F and then G, that's typically going to give you a different result. So swapping the order, it changed the result. So composition does not commute. Okay, what about this next example, f of 5? So this says take our function f and input 5 into it. So here we get f of 5 is equal to 6. We get and so f of 5 is 6. And then we're going to run that through our f function. And well, we've already seen earlier that inputting 6 into our f function now gives us 3. So here, f of 5 gives us 3. Composing f with itself and evaluating that at 5 gives us 3. And then this last example is just to make sure that we're familiarized with this other notation. So g composed with f, and we're going to evaluate that at 3. When we do this, when we write this composition, this is the same as saying g of f of 3. And really what you want to see here is you want to sort of imagine working this inside out. So this is sort of step 1, and then taking that result and running it through G, this is sort of step 2. So f of 3, right? So f of 3 is to take our input of 3 and that leads us to an output of 5. And so what we have to do next is evaluate g of that result, so g of 5. And so g of 5, well, g takes 5 to 1. And so our result here is 1. G composed with f of 3, well, we get 1 out from that. So earlier when we were looking at the two equations, f of x is equal to 3x minus 7 and g of x is equal to x squared minus 1, we looked at the example of composing g of f of 4, right? We looked at this particular example where we had an input of 4. But we can do this in more generality and really describe composition for all input values, not just one particular example. And so here, the composition g of f of x, this really means to take the result of f and input it into our g function. And really when we have these equations here, this expression on the right, this 3x minus 7, that's really describing the result of our f function. This is really describing the output. And similarly, x squared minus 1, that's really describing the output of our g function. And so when I write something like g of f of x, really we can interpret this as saying we'll input our f function into our g function. Right, and since g tells us to square our input and then take away 1, really I can imagine this as meaning square f of x and subtract away 1. And so because f of x is really just 3x minus 7, 3 times the input minus 7 gives us the output for our f function, really this is the same as squaring 3x minus 7 and then taking away 1. Right, so composing these two functions in this way really amounts to evaluating this expression. And so maybe to make our lives easier for this composition, we can really imagine simplifying this expression, right? So here, maybe I'll do this off to the side, 3x minus 7 squared. Really this is the same as 3x minus 7 times 3x minus 7. And so multiplying this out, we get 9x squared minus 21x plus 49. Or in other words, 9x squared minus 42x plus 49. And so our composition, well, that's really the same as 9x squared minus 42x. And so I've got plus 49 and minus 1, so this comes out to be plus 48. Really, this expression here, plugging something into this is really the same. So it gives you the same result as first plugging in that value into f, then plugging in the result from that into g, and then computing that result. So plugging into this function is equivalent to first plugging into f, then inputting that result into g. And so we've already tested this out. We really plugged in or evaluated g of f of 4. And so let's really confirm this for an input of 4. Right, so we figured out that g of f of 4 is going to give us 24 from earlier, right? We did that here. But let's go ahead and do this now for this new composition function. So here, if I plug in to this expression 4, well, what do we get out? We're really expecting to get 24 out, but let's really confirm that. So here we've got 9 times 4 squared, take away 42 times 4, plus 48. So here this is 9 times 4 squared, that's 9 times 16, minus 42 times 4 is minus 168, plus 48. And so 9 times 16, that's 144, and then minus 168 plus 48. And so this is the same as 144 minus 168 is minus 24 plus 48, and then adding these two together gives us positive 24. So we did get the result we expected. And so really, this expression here, it gives us the same outputs as plugging into f, evaluating that, plugging that result into g, and then evaluating that. And so let's get a little bit more practice of doing this idea of composition. It's one thing that shows up again and again. And so I've got 3 different functions here that I want you to combine in various ways. And so let me ask you to pause the video and try and compose these different examples out yourself first, just to get a little bit of practice. But we'll go ahead and go through them together in just a moment. So this g of f of x, so here we've got different functions for g and f. So let's go ahead and try and compute this again. So this is telling us to take our g function as our outer function. We've got f of x as our inner function. And so here I'm going to square my input and then take away 1. So I'm going to square f of x and take away 1. And that's really the same thing as squaring, well, f of x is the same as 1 over x minus 2. So we're going to take 1 over x minus 2, square that result, and take away 1. So when we square a fraction like this, right, if I have a over b and I square this is really the same as, well, I'm going to take a over b and multiply it to itself. And really that just amounts to multiplying that numerator to itself and multiplying that denominator to itself. So really when I square 1 over x minus 2, that's the same as 1 over x minus 2 squared. Take away 1. And so just to get a little bit more practice with fractions, because I know you might be rusty with it, here let's go ahead and really do the simplification, and let's go ahead and really do the subtraction here. And so before I really dig into that, let me go ahead and square out that x minus 2. So here we've got x minus 2 squared, and that's the same as x minus 2 times x minus 2, which is the same as x squared minus 4x plus 4. So that's this denominator here. And the reason that might be useful for us is that that'll tell us what we need to multiply to, or how we need to change this form of this minus 1 here, so that we can subtract these two quantities together. Right, really, we can only subtract fractions if they have a common denominator, and so I just really want to make that denominator very explicit. So this is the same as 1 over x squared minus 4x plus 4, right? That's what we determined x minus 2 squared is. And subtracting away 1, right? In order for us to really do that, we need to make sure that it has a common denominator with our first fraction. And one way I can rewrite 1 so that it has the same denominator as this first fraction is I can rewrite this 1 as x squared minus 4x plus 4 over x squared minus 4x plus 4. So what I just did there was I just imagined, anything divided by itself is going to give me 1, so I can rewrite 1 in this way, right, as this quantity divided by itself. That's the same as 1. But the benefit of this is that now we have the same denominator. And so we can really do the subtraction here. We can really perform the subtraction. And so this is 1 take away. And when we subtract two fractions, we subtract away their numerators. So we're going to have 1, the first numerator, take away x squared minus 4x plus 4, the second numerator. And then we keep the denominators the same. And so this comes out to be, subtracting away x squared is what we get, subtracting away negative 4x comes out to be positive 4x, and then 1 minus 4 gives us minus 3, all over x squared minus 4x plus 4. And then sometimes these kinds of fractions, they can reduce a little bit. And in order for us to identify whether or not they can reduce, we ought to factor the numerator, factor the denominator, and see if there are any common factors. And so I'm going to factor out a negative sign from that numerator to get x squared plus, to factor out that negative sign, I need to factor out a negative sign from every term. So I've got minus 4x plus 3 over, and then here, the denominator, we saw that's really the same as x minus 2 times x minus 2. And so the numerator can be factored further as x minus 3 times x minus 1. And so the numerator now is factored, the denominator is factored, but there aren't any common factors between the two, and so this can't be reduced. This is as simplified as it gets. But this is our expression for g of f of x. Plugging into this function is the same as plugging into f first, and taking that result and plugging it into g. Okay, so let's keep going. The next thing we really wanted to do here was we wanted to evaluate f composed with h of x, right? So here we wanted to evaluate f composed with h of x. And so h was our square root function, and f was our fraction function. So here, write them as maybe I'll just rewrite them, right? So f of x is equal to 1 over x minus 2, and h of x is equal to the square root of x plus 3. Right, so this notation f composed with h of x with this sort of circle operator in between them, I'm not the biggest fan of that. Really, I think it's clearer if I write this f of h of x. And so what this tells us to do is to take our f function and for its input use our h function. Right, and in this case, that means we have 1 over, well, h of x is the square root of x plus 3, and then we still have this minus 2 outside. That can't really be simplified with that square root of x plus 3. Right, that plus 3 is inside that square root, that minus 2 is outside. They don't really interact so well. And so there's not much we can do here. One thing you can do is you can multiply the top and the bottom of this fraction by the square root of x plus 3 and then add it on with 2 at the end. You can multiply that to the top and the bottom to do some manipulation here, but that's not really necessary. That's more of a preference thing. This is sufficient for us. Okay, so let's keep going. The next thing we wanted to do was evaluate f of x. All right, and so f of x was 1 over x minus 2. So we're going to take 1 over the input, take away 2. In this case, we have the input as f of x again. And so this is really the same as 1 over, f of x is 1 over x minus 2. All right, so here really these are meant to represent the same thing, right, f of x. So 1 over f of x minus 2. And so this is, we've got a fraction within a fraction here. How can we possibly simplify this? Well, any fraction, it's okay to multiply the same quantity to the numerator and the denominator. And one thing that can help us out here is actually to multiply the numerator and denominator by x minus 2. And so this is a perfectly fair thing to do. Right? It's kind of the same way that 1/2 is equivalent to 2/4 or to 3/6. Right? I can multiply this number to the top and the bottom, and it's really describing the same fraction. And so if I multiply to the top, I get x minus 2 in the numerator. If I multiply that quantity to the bottom, right, that x minus 2, what happens is, well, that's like saying I'm going to multiply x minus 2 to this first quantity here and then to this second quantity here. Well, multiplying x minus 2 with 1 over x minus 2 just gives us 1. Right, that's like saying 1 divided by some number x minus 2 and then multiplied by that same number x minus 2. Well, that's just going to undo each other and leave us with 1. Now what about this next part, minus 2 times x minus 2? Well, minus 2 times x minus 2 is negative 2x plus 4, right? It's like distributing negative 2 to x minus 2. And so this comes out to be x minus 2 over negative 2x, what is this, plus 5. So this is an expression for f of x. Okay, so the last example I want to do here is to go ahead and compute f of g of h of x. So I want to do this composition within a composition. And so there's kind of a lot going on here. We've got this h function that we're going to input into our g function, and then we're going to input that into our f function. And so maybe let's go ahead and do this intercept first. So here, maybe I'll just do this separately. G of h of x. Right, that's going to be what we're going to input into our f function. So let's go ahead and figure this part out first. So g of h of x, right, g of x was a square function, and take away 1. So we're going to input h of x into this square function and then subtract away 1 from it. And so this comes out to be, well, h of x was the square root of x plus 3. And so if I square that, well then I'm just going to get back x plus 3. And then I still have this minus 1 at the end of the day. So this comes out to be x plus 3 minus 1, that's x plus 2. So that's g of h of x. And we're going to take that and we're going to input that into our f function. Right? So here maybe I'll write down f of g of h of x. Hopefully I'm counting all the parentheses right. I think I've got that right. So here we're saying that we're going to take our f function 1 over, and then our input, 1 over our input take away 2. So our input in this case is g of h of x. Actually, I don't know if I gave myself enough space. Let me try and write this out first. So g of h of x. And so we already figured out that g of h of x is this x plus 2, right? So this comes out to be 1 over x plus 2 minus 2. This is the same as 1 over x. So all that complicated business to just give us out this expression 1 over x. So evaluating into this triple composition is really the same as evaluating this expression 1 over x.